On chair. You are a chair?
Yes.
Just 1 minute.
Okay.
Okay.
Welcome to the blog. And the first speaker will be Agniv, and he will talk about game of arrivals.
Should I sitting last one?
No. Agniv Pandit.
Thank you, Pavel, for the introduction. So consider a cafeteria that opens at 12 o'clock, and every customer chooses when to arrive at the cafeteria. And there are two choices. Like, if the customer arrives early, then she will be served early. But will wait a large amount of time because everyone wants to get the fresh food, and they will arrive early, so there will be a long queue at the cafeteria. And on the other hand, if a customer arrives late, then she will be served late, but wait little, because towards the end there will be the size of the queue will be less in the cafeteria. So there is a dilemma that every customer faces, whether to arrive early or late. And one can model this as a game. And so every customer simultaneously wants to minimize their waiting time and time of service or departure. And Jain et al. In 2011 modeled this by assuming that every customer suffers a cost which is linear in the waiting time and the departure time, and every customer suffers like alpha amount of cost for every unit waiting time and beta amount of cost for every unit delay in service. And this pair alpha comma beta, this quantifies the preference of every customer. And the entrance to the concert is modeled as a bottleneck queue that opens at time 0 and serves at a fixed rate. So in the next slide, I will explain formally what a bottleneck queue is and what we mean by its rate of service. And we want to find the equilibrium behavior in this situation. So, like here we have said that the customers. So the customers are basically the players, and their costs are defined in terms of waiting time and time of service. So in the next couple of slides, I will explain how all of these things are formally defined and how I am defining the customers, the set of players, and what their strategies are, and how their cost functions are defined. So in this slide, I will introduce this fluid model, which makes several simplifying assumptions. But so like the customers can be thought of as every point in the interval 0 to 1. So there are like infinite number of customers, and every point in the continuum represents a customer, and the length of the interval it quantifies the population size of the customers. So in this case, it is 1, and the entrance to that concert can be thought of as a bottleneck queue, serving at a rate mu. So the queue serves a maximum mu mass of customers in unit time. And so what does a bottleneck queue means? So I just said that the total mass of customers is 1. So I can think that customers are arriving at a rate f of t at time t. Then the integral of f of t T is equal to 1 because that's the total mass of customers. And then what happens in the bottleneck queue is that if the queue is busy, then no matter at what rate customers arrive, they will the queue will serve at a rate of mu customers per unit time. That is customers will go out of the queue at a rate of mu, and if the queue is empty, then they will then customers will depart the queue at a rate of mean of mu comma ft. So what that means is that if the rate at which customers are arriving is larger than mu, then the mass of then queue will develop, a waiting queue will develop, and if it is less than mu, then no waiting queue will develop, and customers will simply leave at the rate they are coming. Let's keep this. So like I said, so I am modeling the arrival of customers in the queue by something called an arrival profile. So, which is basically a non-decreasing function of time, and at every time, the value capital F of T represents the mass of customers which have arrived into the queue till time T. And we will assume that this capital F is right continuous, and limit of capital F at minus infinity is 0 and at plus infinity is 1. So what this means is that till mass of customers have arrived, and we will call every such capital F an arrival profile, and this is what a strategy of this game is. That this whole mass of customers is collectively choosing an arrival profile, and once I give an arrival profile, then at any given time there is I can write the mass of customers waiting in the queue is well defined as a function of time. And I mean, this expression is not very important compared to the content of the talk, and it won't be very relevant. So the whole point of this slide is that once I am given an arrival profile, the waiting time and the time of service of every customer is well defined as a function of a time of arrival into the queue. And with this, the cost function, the cost suffered by a customer arriving at time t is also well defined, and this completes the definition of the game. That first the customers collectively decides an arrival profile, and with this, the cost suffered by every customer becomes well defined as a function of their time of arrival. And now I will introduce what's the solution concept of this game. So given any arrival profile, its support is defined as the smallest closed set which has a measure 1, which has a measure 1 with respect to the arrival profile F. So what this basically means is the support is given by the set of all those times at which customers are arriving into the queue, and the definition of an equilibrium of this game is so we define it as an equilibrium arrival profile. So what this means is that so given any time in the support of the arrival profile, and given any other time, the cost suffered if a customer chooses to arrive in the support is always less than equal to the cost it suffers if it arrives outside the support. So as I said before, that the support represents the set of all times in which customers are arriving into the queue, and if an arrival profile is an EAP, then then all the customers which are arriving inside the support, all the customers arriving inside the support suffers equal cost, which is the and all customers arriving outside the support, they suffer the cost at least, which is at least the cost they will suffer if they arrive inside the support. So the customers arriving inside the support have no incentive to arrive outside, and they also do not have an incentive, have any strict incentive to change their time of arrival inside the support. So that defines an equilibrium. Therefore, customers have no incentive to deviate from the EAP. And so one might ask that why, so EAP, that is the equilibrium arrival profile, captures the aggregate behavior of the population of customers. So one might ask why aren't we considering mixed Nash equilibria of this game by considering in behavior of every individual customer. So Jain et al. 2011, they showed that so there is a formal way that, so what a mixed Nash equilibria here means is that there is this continuum of players, and every player in this continuum is picking up a distribution over the time of arrivals, and there is a way of formally defining the resulting arrival profile if every customer is picking up an arrival time like this, and so for every mixed Nash equilibria of this game, this resulting aggregate behavior will be an EAP, an equilibrium arrival profile. And for every equilibrium arrival profile, we can construct a symmetric mixed Nash equilibria of this game, and this implies that these two kind of solution concepts, that is mixed Nash equilibria and equilibrium arrival profile, they are equivalent. From one we can get the other one, and in fact finding an EAP of this game is much simpler.
So what do you mean by symmetric there?
So symmetric means that so in a mixed Nash equilibria, every player picks a mixed strategy, and by symmetric mixed Nash equilibria, we mean all these mixed strategies are same. So it is a known result that in the framework we introduced, that is, there is a single queue and a population of customers arriving there. So it is proved that in that framework there is a unique EAP where all the customers arrive at a constant rate mu times gamma. So this gamma depends on this cost coefficient, that is alpha and beta. So here I forgot writing it. Here gamma is equal to alpha over alpha plus beta. So it is known that in this single queue setting, like the simple setting of a single queue and a mass of customers arriving there, the EAP is unique, and the customers arrive at a constant rate of mu gamma over the time over a given time interval, and it is known that the customers arrive at this that is the support of the arrival profile is an interval in this simple setting. Until now we just considered that all the customers have the same cost function, and they share the same preference over the waiting and the departure time, and one can and in practical situations, the population of customers, I mean different customers can have different preference, and that can be modeled by assuming that there is a partition of the set of customers into n disjoint sets, and every customer in PI has a cost function in which the coefficients are alpha I and beta I, and this alpha I beta I is different for different partitions, and that is the multi-class setting, and some more notations that so let's say the class I has a mass lambda I, and the total mass of the customers is 1, so sum of all these lambda is equal to 1, And now every class is picking up an arrival profile. That is, class I customers arrive by arrival profile Fi, and the overall arrival profile is sum of this arrival profile. So what this capital F is, that is at a given time the total mass of customers of all classes that has arrived into the queue. And with this capital F, like I have shown before, that once I give this overall arrival profile the mass of customers waiting in the queue as a function of time, that is well defined. And with that the cost suffered by a customer of a given class is a well defined function of a time of arrival. And and so using the arrival profile, the cost function for every class is well defined, and we can define a solution concept in this multi-class setting as well. So what it means is that for every class in the support of the arrival profile of that class, the cost is constant, and outside the support the cost is higher. So for every class of customers, there is no incentive to arrive outside the support of their arrival profile. So that is a definition of a solution concept, and it is also proved that in this multi-class setting there is a unique equilibrium arrival profile in which the different classes of customers, they arrive over disjoint intervals, and for every class the support is an interval, and this order of arrival that clearly reflects the preference of these individual classes. Like so for example, if I just have two classes, let's say one is the red group and the other one is the blue group, and without loss of generality, I've assumed that so there were these cost coefficients alpha and beta, and the alpha over beta for the red group is larger than that for the blue group. So what that means is the customers of the red group, they actually prefer arriving, they prefer getting a late service compared to waiting a large amount of time in the queue compared to the blue group. So in the equilibrium also they will arrive later, and the blue group will arrive before the red group, and they will arrive over disjoint intervals. So this is something true for the single queue setting, that whenever I have multiple classes of customers, they will always arrive over disjoint intervals. They cannot arrive over overlapping intervals. And so Giant 2011, they considered only a single queue setting, and later Honappa and Giant considered a tandem network where like multiple queues are connected in series, and they proved that the tandem network is actually equivalent to a single queue whose capacity is the minimum of all these queues connected in series. And so there also all those results known for a single queue setting will follow. Like if there are multiple classes, they will arrive over disjoint intervals. And yeah, they also considered trellis networks, and they showed that with respect to the EAP, like if one only considers the EAP, then the trellis network is actually equivalent to a tandem network, where like, so for every layer of the trellis network, I just add the service rate of these queues, and I construct a tandem network in that way. And again, a tandem network is again equivalent to just a single queue, and all those results will follow there as well. So yeah, Honappa considered the situation where like all the customers who are arriving in a tandem network, they are traveling through the same route only, and we considered two settings where there are two classes of customers. They are arriving in a 2-queue network, and they are traveling through two different routes. So in the first setting, they are arriving at the first queue and they're departing from different queues, and in the second setting, they're arriving at different queues and departing from the same queue. So the first one we call a heterogeneous departure system, and the second one we'll call a heterogeneous arrival system. And in both the systems, we proved the existence and uniqueness of the EAP. When the two groups have unequal cost preference, that is, their alpha over beta ratios are different, and we showed that when the alpha over beta ratios are same, then actually the EAP may not be unique depending on how the model parameters are, and we identified a convex set such that in case the EAPs are not unique, then set of all these EAPs is actually this convex set, and yeah. So I will mention some of the interesting observations about the EAP for the heterogeneous departure system. So there we observed that. So here one observation is that there are these two queues, and if the second queue has a capacity larger than that of the first queue, then the second group, that is the blue group here, which is traveling through both the queues. So after it passes through the first queue, it will arrive at the second queue at a capacity less than equal to its service rate, because mu2 is less than equal to mu1. So the whole thing will be equivalent to the situation where only the first queue is present, because the second group will not face any delay in the second. So using the results known for the single queue setting, we can say that the two groups will arrive over disjoint intervals. So one natural question is so here I said that mu2 is greater than equal to mu1, then this non-overlapping structure will be there in the EAP. So one natural question is, so if I now start pulling down the capacity of the second queue, then up to what threshold will this disjoint arrival structure remain? And we prove that, and there is a threshold which is given by mu1 times minimum of 1 and gamma 1 over gamma 2, but gamma is basically the cost preference of the ith group, and if the capacity of the second queue is above this threshold, then the two groups will arrive at disjoint intervals, and once mu2 falls below this threshold, then the intervals over which these two groups are arriving will start to overlap. So that is illustrated in these two figures. That is, if mu2 is larger than this threshold, then the red group and the blue group they are going to arrive in disjoint intervals, and once mu2 is strictly lesser than this threshold, then they will overlap, and the order in which they overlap, that is decided by the preference of the two groups, and also all the model parameters like the capacities and the population size of the groups. For example, if the population size of the second group is significantly larger than that of the first group, then the first group will then the second group will arrive over a large interval, like shown in the figure, and the first group will arrive somewhere in the middle. So this is in the regime where the second group has a mass larger than that of the first group, and in case and in the other regime where the first group has a mass larger than that of the second group, the intervals will still overlap, the order in which they arrive, that clearly reflect their cost preference. And this is exactly the same that similar to the one that happens in the single queue setting, like the group that prefers a late service compared to waiting a large amount of time in the queue, they will arrive late, and the other one will arrive early. And another interesting observation is, so this is all when the two groups have unequal cost preference, and we have also observed that if the cost preferences are equal, then the EAP is not necessarily unique, and in fact it is given by a convex set, and the two extreme and both these arrival profiles actually belong to that convex set, and they kind of represents two extreme boundaries of that convex set, and there are many, uncountably many nonlinear arrival profiles in that convex set. And till now, in all the scenarios that we have considered, we have seen that players of every class arrive over an interval. That is, like in all the arrival profiles, the supports are intervals. Like this, the arrival profile that is increasing over an interval, and outside that it is just constant. So one might expect that such a statement is generally true, but there is a situation where a group of players can divide their arrival over two disjoint intervals, even with a simple modification to a 2Q network like this. So this is the other setting that we have considered, and there for this particular parametric regime, we have seen that. So here if we slowly increase the mass of the second group, if it is too less, then there is this interesting phenomenon that all the customers in this red group, they gather in the queue before time 0, which is typically not observed in single queue settings. And if we slowly increase the mass of the red group, then after a certain threshold, a certain fraction of the mass of the red group arrives after time 0, but they arrive after the blue group has finished arriving, and this is something that isn't observed in single queue networks.
And this is unique, right? So
these are all unique. These are all unique profiles. And this is a very surprising observation. And we have seen that even in simple instances, like there is a 2Q network and two groups arriving, there can be like large number of possible solution structures. For example, in the first instance we considered, there are 5 different possible structures of the EAP, even when the EAP is unique. And in the second instance we considered there are 8 different solution structures possible. And assumptions such as every class arrives over an interval doesn't hold generally. Like a class can arrive over a broken interval as well. So even a bit of heterogeneity in a small network, finding all possible structures of the EAP can be hard. And we considered this game only in this one-shot settings. So a future direction can be what happens when this game is played repeatedly. Is there any natural update rule such that if every customer is updating their arrival time or their mix strategy using that update rule, then they minimize the cost in the long run, and where does such update rules converge? Or maybe not customers are individually updating. Maybe there are multiple groups and every group is updating their individual arrival profile, and there is this known framework of isocost curves which were introduced by Lindsay, and And this framework explains the equilibrium behavior only in single hit setting. So a natural question is, can one extend this for this heterogeneous networks? So all of these are open future directions. Yeah, thank you for listening.
So, any questions? Great, so let's bring